Welcome back, students. Now, one compartment open model extravascular administration. We are going to study the determination of pharmacokinetic parameters. In the last class, we had done up to the derivation, and this was the final expression. C is equal to this term. Now, the pharmacokinetic parameters which we have to determine are Tmax and Cmax. So, how do we determine them? Let us do it one by one. First, let us consider the case of Tmax. Now what happens is that at Cmax or Tmax, the rate of absorption is equal to the rate of elimination, which means that the term KAXA is equal to KEX. That is rate of absorption, the absorption term is equal to the elimination term. Or we can also say that dC by dt is equal to 0, or the rate of change in concentration is going to be 0. There is no change in concentration at that particular peak point or the Cmax. So how do we get the value of dC by dt? Consider this as equation 1, or the equation which was determined in the last derivation. Now on differentiation of this equation, what do we get? dC by dt, C becomes dC by dt is equal to Ka F x naught Vd, in brackets we have the same thing, Ka minus Ke. Now over here minus Ke e to the power minus Ket. This expression changes slightly because of the differentiation. Ka e to the power minus Ket. Now on simplifying this expression, what do we get? We get Ke e to the power minus Ket is equal to Ka e to the power minus Kat. The remaining part is simplified. This is what we get. Now, on converting this into log form, what do we get? We are going to get log Ke minus 2.303 divided by Ket is equal to log Ka minus 2.303 upon Kat. This is the form in the equation in the log form. Now, what we will do is, we are going to consider this T time as the Tmax. If this time is equal to Tmax, on further simplifying this equation, we get Tmax is equal to 2.303 log Ka divided by Ke, this whole divided by Ka minus Ke. So this is the final expression for the value of Tmax in case of extravascular administration. Now similarly, the value of Cmax is going to be F x naught divided by Vd e to the power minus Ket. This expression, we do not have to derive this, that is not required at your level, at the DPHARM level. Now, we get this expression from this value, Ka, this term, and this term. The reason is that at the Cmax, both Ka and Ke become equal. So at this point now, the elimination in the post-absorption phase, the concentration or the change in concentration is going to be dependent only on the rate of elimination. That is why now we are only considering the factor Ke and not the term K. Now let us simplify this further, because what happens is that at Tmax we know that Ka is equal to Ke, and also T is equal to 1 upon Ke. This has been done previously also. T is equal to 1 upon Ke. Now substituting this value of T by 1 upon Ke, what do we get? Cmax is equal to F x naught upon Vd e to the power minus 1, because both Ke and this 1 upon Ke get cancelled out. The value of e to the power minus 1 is F x naught upon Vd. This value e to the power minus 1 is 0.37. This value is 0.37. Now, this has a clinical significance, and what is the significance? And see, in case of intravenous administration, we were considering that the bioavailability is 100%. Yes, but in case of extravascular, it is not 100%. So what is that value? Generally, it is seen that it is equal to this fraction 0.37. Now, this 0.37 is the fraction of the drug which is absorbed systematically, which can be correlated to 37% of the drug being absorbed systematically as compared to 100% of intravenous administration. Okay, so for this time we have the value of Tmax and the value of Cmax. We had the general expression in the previous class, in the previous lecture, the value of concentration. Now we have the value of Tmax and Cmax. This is the complete derivation of one compartment open model extravascular administration when the drug follows first order absorption and elimination pattern. In the next class, we shall study about the methods to determine Ka. Okay, we already know how to determine the value of Ke. See, the value of Ke, as previously discussed, can be determined by plotting a graph of log C versus time, where we get a straight line and the value of slope is always equal to minus Ke upon 2.303. So the value of Ke can be easily determined by making a semi-log plot of log C versus time. But for determining Ka, the absorption rate constant, we have two special methods, and the methods are, first is the method of residuals and the second is the Wagner-Nelson method. Now, Wagner-Nelson method I have already discussed in one of the lectures. In the next class, I shall discuss about the method of residuals. Till then, you can just memorize this, study this, go through this. If you have any doubts, do contact me. Thank you.